Hi everyone. What we're going to watch right now and work through is a process for discussing oblique asymptotes. And so what we're going to do is we're going to add in a third type of asymptote that you can encounter on a rational function. And then we're going to actually go through the full curve sketching kind of algorithm, if you want to think about that full process. So take a look at what you have on the screen now, and we're going to add in an oblique asymptote. So we already have in our back pocket vertical and horizontal. And what we're going to add in is what you see are referred to as oblique or slanted asymptotes. So when we refer to oblique, really what we're talking about is neither horizontal or vertical. So if you're thinking about it as a line, it's a line that's got a slope, right? It doesn't have a slope that's undefined. It doesn't have a slope that's zero. It's got a slope to it. So what we're talking then about an oblique asymptote is a slanted line that a graph approaches but does not touch. So we're going to work our way through maybe a little bit more of a complex sort of situation dealing with that asymptote. So what I've put on the screen now is an example of what an oblique asymptote could look like. So for this type of function, I've drawn the function in gold. You'll notice that it has a vertical asymptote, and I just called it at x equals c. And then you'll notice the red line, that dotted line, would represent an oblique asymptote. You'll notice that I've written out the equation of that line as like y equals mx plus b. We should all be good with y equals mx plus b from grade 9. So even if I was just to look at that red line right now, I know that my b value would have to be positive because I have a positive y-intercept. My line was falling to the right, so my m value would be negative. Like, we already have all those properties. That stuff is background. However, when we start to tie it all together, though, we're now starting to see, okay, vertical asymptotes, slanted asymptotes, or oblique ones, can now come together to form a rational function. So let's break down then the process for finding an oblique asymptote. There's a shrunken version of what that curve would look like above, and I want you to give the blue sentence a read. It's got a little bit of English in it, it's got a little bit of mathematical notation in it, but I want you to give that blue statement a read. So pause the video now. Okay, and we're back. I'm hoping that that blue statement makes sense to us. And I've tried to match up the colors as best as I can with the original curve, which that full graph. So all that says is the rational function f of x, which is g of x over h of x. So that's just some expression over another expression. The difference between f of x and mx plus b approaches 0 as x increases or decreases without bound. So all that refers to the difference between the curve and the asymptote, the gold and the red, approaches 0 as x gets bigger and bigger and bigger in either direction. So that is a very formal way of saying that the y value of the curve compared to the y value of the asymptote, the value of the function versus the value of the asymptote, approaches 0. So I'm going to just mark up that diagram a little bit so we can see that this is really just stating the obvious for us. That if I was to take this particular x value, I would notice that that gold graph subtracted from the red graph would give me the length of that green arrow. That's the distance between them, or the difference between their y values. And as I start to move to the right, that difference gets smaller and smaller and smaller. Now, you just know that as the nature of a curve approaching an asymptote. It gets closer and closer and closer to it without touching it. That's all we really mean when we say approaches a value of 0. So, I want to now take that blue statement and let's turn that into notation. And so what you'll notice is I just kind of slid everything else up again. But now I've included what would be the algebraic translation of that blue statement. So the blue is predominantly in English. That green is now our algebra. There's our notation. So all that says is, as we go forever and ever and ever in either direction, there's my limit as x approaches positive, negative, infinity. The difference, meaning subtraction, between f of x and mx plus b, the asymptote, approaches 0. So it equals 0 for the limit. That's all we're talking about. And as we said, that's pretty obvious. Okay, how do we now go through to find that oblique asymptote? What you see on your screen now is the process for us to do that. Now, you'll also notice that I put this big red wavy line down the middle because there's really only one step for us to find an oblique asymptote, and it's actually probably the easiest one for us to find. You just have to do step 1. Determine g of x divided by h of x. So what that means is actually do the division. So what you see in brackets is we're just going to use long division to find that asymptote. Now, step 2 becomes an important feature for us. It becomes an important feature for us to be able to obviously state the asymptote, but more importantly, really understand what's going on with that curve. So when we take a look at that process, you'll notice that the answer we get when we do the division, our q of x, that becomes the equation of the asymptote. We just have to write it as an equation. So that means we're going to start it off with y equals. More importantly, I want you to take a look down at what's going on with the remainder. Because that r divided by h of x is what's key for us to being able to find an oblique asymptote. Yes, we get that, at least just because I've told you that the quotient is the asymptote. But the reason why my curve doesn't hit that asymptote, why it never equals that asymptote, is because when I do the division, there is a remainder. And so really what we see then is that if we examine the limit as x approaches positive or negative, and that should say infinity, then r divided by h of x must approach 0. So the remainder, when we did the division, is going to become smaller and smaller and smaller, approaching a value for 0 as we go on forever and ever in both directions. Okay, that might seem a little more complicated than what it is. We're going to jump in and we're going to work with oblique asymptotes, and I think that'll help us to see the process. One big conclusion that I want us to make, and this is a big issue for us as we move forward, is I hope that we see that since my quotient, the answer I get when I divide, becomes the equation of my linear asymptote, then that is going to force us to recognize when we have an oblique asymptote. If my answer is going to be linear when I divide, then therefore g of x, the expression that I have on top of my fraction, must be 1 degree higher than h of x, the expression I have on the bottom of my fraction. And so if I was to try to explain that a little further, if my original function had a cubic on top, then if there was going to be an oblique asymptote, my denominator has to be 1 degree smaller. And so we could see that if we took a cubic and we divided by a quadratic, that would give us a linear quotient. If I had an original function that had a quadratic on the top, then I would need to have a linear on the denominator, 1 degree smaller, in order to get my linear quotient. Therefore, if I have f of x and the highest power of x on top is 1 and the highest power of x on bottom is 1, then I cannot have an oblique asymptote, as when I do my division, I will not get a linear divisor. Quotient. So this should bring up an awful lot for our conclusions about what types of asymptotes must exist for what types of functions. And so let's take a look at problem 1 and let's work through this one. I want to determine all asymptotes for that function. Now, there's a few things that we should kind of tie together here so that we can see, well, what are the combinations of asymptotes that can occur within a function? Okay, well, the first thing we note is that to have a vertical asymptote, then your fully simplified function has to be a fraction where the bottom, that denominator, can equal 0. So anytime that I have a fraction where my bottom can equal 0, then I'm going to have a vertical asymptote. Well, we examined for horizontal asymptotes that your highest power of x has to be on the bottom. So I know that my denominator, I'll call it d again, that d must equal the highest degree. And then we also notice that for our oblique asymptote, that my highest power of x has to be on top. Like, in fact, my numerator must be 1 greater than the denominator. And so if I was just to examine those 3 in terms of scenarios, I'm hoping that we can see that we have a bit of a problem here. That these 2 asymptotes cannot exist within the same function. In order to have a horizontal asymptote, if my highest power of x has to be on the bottom, but in order to have an oblique asymptote, the top has to be 1 degree higher than the bottom, then both of those things cannot exist at the same time. And therefore, you never have to worry about finding a horizontal asymptote and an oblique asymptote within the same function. Now, let's say I was to ask you the problem that we asked in 1. And I'm just going to put a little wavy line down here. We should be able to read the function, look at it, and figure out what asymptotes we have. Okay, the first thing we always do is we try to simplify. So I'm going to look to factor the top. And when I factor the bottom, or look at the top factored and examine it based on the bottom, I notice it is fully simplified. Okay, because it is fully simplified, can we make the bottom equal to 0? Yes. So we do have a vertical asymptote. Where is the highest degree? It's on top. By how much? 1. By 1 degree more. Therefore, you do have an oblique asymptote. In order to have a horizontal asymptote, your highest degree has to be on the bottom. It does not. So we do not have a horizontal. If I was ever to ask you question 1 on an evaluation, determine all asymptotes, you don't even have to mention that there is no horizontal. You can just use your background knowledge to state the ones that exist. You don't have to state any asymptotes that do not exist. So, I am going to just wipe all of this stuff out. Because the question just says determine all asymptotes. Well, we can pretty quickly go through and say I have a vertical asymptote that exists at x equals 2. Okay, how do we find the oblique asymptote? Well, if you recall, the oblique asymptote is found by performing the division. So we are going to take x squared minus x minus 6 and divide it by x minus 2. So we go through that division process. Now, this is never required, but some people do like to write out that f of x is your quotient, x plus 1 minus, or add on the negative of the remainder out of the divisor. This was the notation that we stated earlier. What's important for us to know, that is your asymptote. It's just not stated in the form of a line. So if you then included the red and said therefore y equals x plus 1, then if I was to ask you question 1 on a test, all you would ever have to show me is the red. Now, what does restating it in the orange do? It just allows us to see that that's the remainder, and that's the amount that if we ever were to examine the limit as x approaches plus or minus infinity of 4 over x minus 2, we could examine that limit. We know it must approach a value of 0 as x gets bigger and bigger. That's all. But you take a look at the red, and that is our process for being able to find an oblique asymptote. It's pretty straightforward. Okay, where I want to go next then is I want to go through a couple full curve sketches. So this is where we're going to start to go back to, you have some stuff in your back pocket, and I want us to pause the video as much as we can and try to attempt as much of this on our own as possible. So let's jump into the next one. Okay, what you see in question 2 is we are going to use intercepts and asymptotes. And so as soon as it says that we are using asymptotes, that means that you get all of your nature of the curve to sketch. And there is our first function, y equals x squared plus 4x plus 3 divided by x minus 2. So if you're looking to match up with me, I'm going to go through and I'm going to find intercepts first, and then I'm going to find asymptotes. So what I'd like you to do, go ahead and pause the video. Give this one a shot on your own and try to find all the information you can. We'll see if we match up in the end. Okay, give it a shot. Okay, we're back. So I'm going to work my way through then, start to finish, finding all this key information. So the first thing I'm going to do, take a look. I notice that my top factors. Now, pretty quickly I could have seen that it wasn't going to factor into anything that included an x minus 2. So at the very least I know that that function is fully simplified. Okay, I told you I was going to find my intercepts first. So to find my intercepts, then maybe I find my y-intercept first, because then I just have to sub in x equals 0. And so if I go back to the white version, my simplified version, then when I replace all my x's with 0, I get negative 3/2. Now I'm going to find my x-intercept. That means my y value equals 0. And this is where I would argue to you, take a look at the purple. I know that to make a fraction equal to 0 means that the top is equal to 0. And I've already factored my quadratic, which allows me to find my x-intercepts of negative 3 or negative 1 pretty quickly. Okay, now we need to take that information, and now we're going to jump in and start finding our asymptotes. So what we want to look at first, look at the equation of the function and figure out which asymptotes this curve includes. Now, what you see in the top left corner is there's both forms of my function, whether it be in factored form or in simplified form. What I'm going to do is I'm going to examine the first type of asymptote that we might have, and we might consider that being our vertical asymptote. And we notice that our vertical asymptote would occur at x equals 2. So now I need to address my nature of my curve. I need to approach 2 from the left. And all I'm going to do is I'm going to walk through finding the limit using the different forms, because I do want you to see that to find a vertical asymptote's nature of the curve, there's maybe a benefit or a drawback to either form. Like, neither one is entirely better or entirely worse. So, let's examine the left side of approaching 2 with our simplified form. Okay, we should be so fast to go through this because we've done this for a couple days now. We should be pretty automatic. Okay, so close to 2, I can treat it like it's 2. So I'm going to sub in 2. 2 squared plus 4 times 2 plus 3 all over 2 minus 2. Okay, I'm going to simplify that, and I have 15 on top, and I have a 0 on the bottom. I love the 0 on the bottom. That confirms that that's my asymptote. However, now I need to remember that I'm not really subbing in 2, I'm really subbing in something a little bit less than 2. I don't care about the 15 on the top. Either side of 15 is about the same. I do care about that 0 on the bottom. So if I'm subbing in something a little bit less than 2, then that's a value smaller than 2. And so if I sub in smaller than 2 and then subtract 2, I'm always going to get a negative value. That means my denominator is that negative bit, and so when I calculate that, I get to negative infinity. Okay, not too bad. I want to take a look now at maybe tackling the other side, the right side limit, but I'll use the factored form, just so we can see what that looks like. Okay, so close to 2, I can treat it like it's 2, so I'm subbing in 2. That gives me 5 times 3 all over 0. Which gives me 15 over 0. For some of us, we're not going to goof up on the 15 as much because actually multiplying those, subbing it into the factored form is a little bit easier. Okay, we know that those zeros on the bottom aren't really zeros, they're really bits. So we have to examine subbing in a little bit to the right of 2. Well, to the right of 2 is bigger than 2. And so if I take bigger than 2 and then subtract 2, that will always give me a positive value, which tells me that's always a positive bit, and that's going to take me to positive infinity. Okay, there's the nature of the curve addressing my vertical asymptote. Okay, now we need a little confirmation on what the other asymptote was. Okay, so hopefully we took a look at that and we saw that the top was 1 degree higher than the bottom. We can see that in our simplified form, and so therefore we have an oblique asymptote. Okay, well, how do we find our oblique? We have to do the division. So I'm going to divide that out then and see what my quotient is. So I'm going through and dealing with that long division, which we should be pretty automatic on by now. And therefore, y equals x plus 6 is my asymptote. Okay, so what I have then is all my information. The only thing left to do is to put it all together into one picture. So next, we're going to actually produce the graph. Okay, and so what we'll see then is just all of our key properties listed out on the side. That's just so I can fit it onto this screen. By no means do you have to write out those properties. And now we're going to go through and we're going to produce that graph. So first thing I always start with are my asymptotes. So let's go ahead and put on our vertical asymptote at x equals 2. So estimate what you think or want 2 units on your x-axis to represent. We will put that on. Now, I did not just generically pick that 2 and estimate it. I also took a look a little bit at what my intercepts were to make sure that I have enough space to be proportional on my graph. Now that I have that, I'm going to put my nature on. I know that to the left of that, I'm going down. To the right of that, I'm going up. Okay, now I'm going to put on my oblique asymptote. Well, I notice in that oblique asymptote that I've got a couple features. I know that that is my y-intercept, and I know that my slope is 1. So a slope of 1 means I've got my perfect 45-degree line. Then maybe I go through and I estimate that this might be 6. And if that's 6, well, that doesn't seem very proportional to my 2. Okay, well, if I get rid of that as my 6, and I then said, well, that was 6, I want us to notice one key thing about our picture, that as I go to put on my asymptote, my perfect 45-degree line might make it very difficult for me to put on all of my graph. Okay, and so what we're going to do is we're going to backtrack significantly, and you're going to see why in a moment I might want to reconsider all of my information at one time. So let's kind of reset a little bit, and we'll come back in with the information we found. Okay, now as I scan through all my values, I notice that I've got x-intercepts at -3 and -1. I have to be able to put 2 on my x-axis. And on my y-axis, I need to get up to 6 with some space to be able to see. I don't want 6 to be right up at the very top of my grid, my set of axes, because now I won't be able to see what was beyond it. So, with all of those things in mind, I'm going to choose based on the largest value. So when I take a look at that oblique asymptote, I've got that y-intercept of 6. I might say that maybe this is 6 on my y-axis. So now when I go through and I do my perfect 45-degree line, or as best as I can eyeball it, to be able to put on that asymptote, I don't mark anything on that asymptote on the grid, so I'm not going to label the y-intercept at 6. There is my asymptote. I will now label my asymptote. That's going to affect where I put my position or my vertical asymptote of x equals 2 at. So now I'm going to be a lot closer to that x-axis. And so maybe this then becomes my vertical asymptote at x equals 2. Okay, now I'm going to go through and I'm going to address the fact that I have to the left of my vertical, I'm going down, to the right of my vertical, I'm going up. Now, one key feature for us, and it's maybe already popped into your head a little bit. Do we have to address nature of the curve with an oblique asymptote? The quick and easy answer is no. It's not within our course. So when we go through the curve sketch, there will always be other pieces of information there for you to draw your conclusion on. And so, as one example, can we take a look right up at the very top of that graph? And I'm just going to go through and highlight the area in green. We're going to have a branch of our function that's going to exist up there. And I think we can already piece together how it's going to exist. So let me get rid of all of that highlight. And now let's go through and actually draw our conclusion. Well, if my curve is supposed to go up where I see that blue arrow, and it needs to approach that asymptote, then I need to have, my curve approach like that. And so it makes sense then for me to draw the conclusion that the actual curve I'm talking about would look something like the gold. So I'm going to have this little branch. It's not really little, it's infinitely large. But all I'm going to see in this portion of my picture is this little portion of that branch up in the top. Okay, I do have a couple other pieces of information that I can use. I have my intercepts. I know that at -3 and -1. So there would be my -1. -3 would be about there. If I was to do a quick peek on that red, I know that the x-intercept for that red line would be at -6. So I know I have to be about halfway. My y-intercept is then at -3/2. So -1.5. I might exist somewhere down there. Well, I think we can piece together the way our other branch goes on this function. I have to follow that nature of the curve as I approach the vertical asymptote. I then have to cross through at that y-intercept, at that x-intercept, at that x-intercept, and then slowly approach that asymptote. What you see in gold then would be a pretty decent sketch of what that function would look like. And there's how we tie everything together. Okay, if you need to go back and look at any parts of that function, then pause the video and hop back and take a peek. Otherwise, we're going to move on to one last function. And this one's got a bit of a doozy to it. Okay, I'd like you to take a look at B, and I'd like you to go start to finish. So, same thing as before. We're going to pause the video, and the second you think you know where to go, I want you to try it on your own. But I'm going to assume that I'm just putting up a solution to this, and you have already paused, attempted on your own, hit a snag maybe, watched a bit of the video. As soon as you found out where to go, you paused it again. You then tried to do the rest on your own. I'm assuming you were making the most out of this lesson. So all I'm going to do then is post a complete solution to it. Okay, let's get things going. That is fully simplified, so the first thing I'm going to do is I'm going to hop in and find my intercepts. To find my y-intercept, that's nice and easy. My x value equals 0. And so if I sub in all those zeros, I get a y-intercept of 3. Okay, my x-intercept is found by making my y value equal to 0. The only way a fraction equals 0 is if the top equals 0. And I can solve that for one x-intercept at -3/2. Okay, now I need to address my asymptotes. Well, I take a look at that, and I should notice that I'm going to have two asymptotes. The first one that I know is there is a vertical asymptote. What makes the bottom 0? We'll set the bottom equal to 0. X equals -1/2. So I'm going to go through and I'm going to examine the nature of my curve as x approaches -1/2 from the left into that function. And I'm going to examine the limit as x approaches -1/2 from the right. And I'm just going to write f of x to speed things up. Okay, I'm making my substitution so close to -1/2, I treat it like it's -1/2. Well, when I sub that up into the top, I'm going to get -1 plus 3, that's a 2. On the bottom, I'm going to get 0. Perfect, that's what I needed. But now I need to remember I'm not really subbing in -1/2, I'm subbing in numbers a little bit to the left of -1/2. That is bigger negatives. So when I sub that in to 2 times a bigger negative, I'm going to still get a bigger negative. And so when I add the 1 onto it, I'm not going to get enough to turn it back. It's still going to be a negative. And so if I take 2 and I divide it by a really small number, always getting smaller, and a positive divided by a negative is a negative. Okay, now I jump into the right side. Well, I'm going to sub in so close to -1/2, replace it with -1/2. There's my 2 over 0. But I know it's not really going to be -1/2. It's going to be a value a little bit to the right of -1/2. That is a smaller negative. So when I sub that in for x, 2 times that smaller negative is going to give me a smaller negative. When I now add 1 to that, that adding of 1 is going to be enough to change that small negative into a positive value. And so when I calculate that, I get to my infinity. Okay, we get to that point, and now we should all be able to predict what the other asymptote will be. Okay, so what we see then is the highest power of x is degree 1, and that exists on the bottom, and so therefore I have a horizontal asymptote. And so I'm going to examine going forever to the left as x approaches -infinity, and now at the same time I'm going to divide through by the largest power of x. So I divide the top, 2x by x, 3 by x, 2x by x, and 1 by x. And now I go through and I imagine subbing in huge negative values. Well, I have nowhere to sub it in for that 2. Any fraction where the top is constant, the bottom becomes bigger, approaches 0. Nowhere to sub it in for the 2. And 1 over x is the same situation. The top is constant, the bottom is always getting bigger, approaches 0. Now what I need to do, piece together my signs. So on the top of the overall fraction, I have a positive 3, and I am subbing in huge negatives for x. So I'm going to have a positive 3 divided by a negative number. That tells me that I'm going to have a negative bit. On the bottom, the same thing. A positive 1 divided by a huge negative number, another negative bit. So I'm just going to get rid of all the color up in the function and just replace those with our negative bits. Okay, so close to 0, we can treat them like they're 0. So that becomes 2 over 2, which I don't even think we need to write in. Instead, 2 divided by 2 is 1. So at the very least, what we just found is we go forever to the left, y equals 1 is my horizontal asymptote. But now we know that we have to examine the nature of the curve. Okay, well, what's the nature of the curve? Well, if I take a look on top, I have 2, and now I am subtracting a bit. So if I take a little bit off the top, then I make the top smaller. Well, making the top smaller reduces my number of pieces. It makes the overall value of the fraction smaller. Okay, I take a look at the bottom. Now, when I subtract a bit on the bottom, that makes my bottom, my denominator, a little bit smaller. Well, if I divide by a smaller value, then that makes my fraction larger. Okay, maybe we're starting to see an area of confusion here. The top arrow, or sorry, the top bit made the value of my fraction smaller, but the bottom bit made the value of my fraction larger. So now I'm having a tough time trying to figure out, well, then is the value really a little bit bigger than 1 or less than 1? Notice this is all caused because I was subtracting a little bit off the top and subtracting a little bit off the bottom. Notice if this bottom had been a plus, for instance, they were opposite signs, that one's relatively straightforward. But because it was the same sign in each case, that's what makes the difficulty. Okay, so what do we do in that instance then? Well, then we're forced to take a look back and see where the bits came from. And this problem actually becomes pretty simplified in this case. If you look back up to our first limit line where we divided by the largest power of x, then we can see on the top, I actually have 3 x's, whatever size x are. On the bottom, I actually have 1 xth. Notice that those denominators are the same thing. They're both x's. And so when I look at the numerator on the top, I notice that I have 3 of them, where my bottom, I only have 1. So imagine that x was like 10. This is telling me that my bit on top is 3/10, where my bit on bottom is 1/10. Notice that my bit on top is larger. So what that's telling me then is the size of the bits matter. So when I look back up into my function, I notice that the top bit is larger than the bottom bit, so the effect that the top bit has is larger than the bottom bit. And therefore, it dominates the other. So when we see up on top that by subtracting that bit, the value of the fraction decreases or goes down, then that tells me that I really have something that is a little bit smaller than 1. And where are y values smaller than 1? They are below. Okay, I want you to notice that we encounter then maybe a little bit of difficulty if we see that those effects on the fraction are opposite. But we just go back and we take a look at the sized bits. So let's do the same thing examining the limit as x goes to positive infinity. We're now going forever to the right. I'm going to write this in just so we can see it very clearly. Okay, we're imagining now subbing in huge positive values. Well, nowhere to sub it in for 2, that fraction approaches 0. Nowhere to sub in for 2, that fraction approaches 0. Now we take a look for our signs, and because I have a positive 3 over a big positive number, I'm adding a bit, and a positive 1 over a big large value, I am adding a bit. So when we calculate that based on those being zeros, we get a y value of 1, and therefore we confirm that our horizontal asymptote is y equals 1. But now we need our nature. So we look back up on the top and we say, well, if I am adding a bit to the top, that's more pieces. That means my fraction is larger. Then we take a look on the bottom and we say, well, if I add a little bit to the bottom, I'm dividing by a bigger number. That makes my fraction smaller. Notice those two arrows are fighting against each other again. One saying bigger, the other saying smaller. So I have to go back and I have to look at the bits. So which bits are larger? 3 of something or 1 of that same something? Clearly it's 3 of something. And so that top bit dominates the bottom bit. And so by that top bit, that means that we have a larger value than 1. And where are larger values than 1? Above. Okay, that gets us to the end of what could have been a pretty complex function. Now what we have to do, take all the properties, put it together as a sketch. So what I want you to do is pause the video now and make sure that at the very least we can take a set of properties and produce a sketch from it. Okay, pause the video now. Now, okay, so hopefully you can see everything that we've got on the left side. And what we're going to do is we're going to take all those properties and we're going to go through and we're going to produce our sketch. So, same thing as before. I notice I've got a y-intercept of 3, x-intercept -3/2. My vertical asymptote's -1/2. My horizontal asymptote is at y equals 1. So I'm pretty good in terms of my scale. So what I'm going to do is I'm going to start with my vertical asymptote. It has to be at an x value of -1/2. So it's going to be a little off the y-axis. And I notice that to the left of that, I'm going down, and to the right of that, I'm going up. I also take a look at my horizontal asymptote, and I notice that that's at y equals 1. And so I'm going to put on my horizontal line at 1. I need to label that asymptote. And I notice that forever to the left, I'm coming from below. And for everything to the right, forever right, I'm coming from above. Okay, now I can think about where my intercepts would lie. And so that means I need a y-intercept up here at 3. And I need an x-intercept at -3/2. And so if I was to put all of that stuff together, then I can pass through this y-intercept and increase, and then come around. Oh, yikes, that's getting a little too steep. And then come around and approach that asymptote like that. I can then see that I need to go through the x-intercept and approach, and then approach that vertical asymptote. And so if you gave me the gold with those purple labels on your intercepts, you have your asymptotes labeled, then you have a pretty good sketch. Okay, there we go. So your job now is to just keep going through this whole sketching algorithm and be able to take your rational function, break it down into its parts, find your asymptotes, examine nature of the curve and end behavior, and I think we'll be great. Okay, jump in and get some practice. Good luck.